Imagine a water treatment plant, right? The pressure valves are just quietly maxing out.
Yeah, pushing the industrial pipes to the absolute brink of rupturing.
Exactly. But if you look at the facility operator's computer screen, all the digital dials are green, the flow rates look perfectly stable.
Everything appears completely fine to the person in charge.
Right. Today, we're diving into what happens when the digital window into our physical world gets hijacked. I mean, you wake up, turn on the tab, flick a light switch, or, check a phone made in some highly automated factory.
And behind every single one of those actions are these invisible screens quietly running the modern world.
We are entirely surrounded by this hidden operational infrastructure.
We really are. And those screens, the software running them, they're often the only layer of translation between, complex physical engineering and human control.
Which is exactly our mission for this deep dive. We are exploring the HMI, or the human-machine interface, in industrial automation.
It is a massive topic.
It is. So based on the stack of sources we're unpacking today, we've got NIST security guidelines, PIATU standards, even some engineering manuals from ABB. We're going to examine what the HMI actually is.
And why it serves as the critical heartbeat of these industrial control systems.
Right, and exactly how engineers are trying to build, digital fortresses around it. Because if you're used to typical IT security, where a breach just means a stolen credit card or a leaked database.
This requires a total mindset shift.
Yeah, completely. We are talking about cyber threats that manifest as physical, real-world disasters. So, this is one of the most high-stakes tech conversations you can probably listen to.
Absolutely. But to really understand the security threat, we first have to sort of map out the architecture of an industrial control system, or an ICS.
Okay, let's break that down.
So when you look at the NIST guidelines, they outline this highly stratified environment. At the very top level, spanning across whole facilities or even multiple geographic locations, you have SCADA.
Which stands for Supervisory Control and Data Acquisition.
Yeah.
Right.
Exactly. That system is aggregating just massive amounts of telemetry from everywhere all at once.
But then down on the actual factory floor, you have the PLCs, the Programmable Logic Controllers.
Right, the boots on the ground, basically.
Yeah, from my reading of the Patreon guide on smart manufacturing, these are the ruggedized hardware devices that are physically wired into the machinery.
They're the things actually doing the work.
Opening the physical valves, spinning the turbines, regulating thermal controllers in real time.
And they do that based on local logic. But the challenge here is the communication gap between that high-level SCADA system and those granular PLCs.
Because they speak different languages, essentially.
Pretty much. I mean, a PLC operates on raw electrical signals and basic memory registers. It's really just processing inputs and outputs at a polling rate of milliseconds.
So a human being cannot read a stream of hexadecimal values flashing past at that speed and make any sense of it.
No, definitely not, let alone operate a power plant safely based on that raw data.
So this is where the HMI sits. It's the visual interface bridging the human operator and the machine.
Exactly. It's the translator.
And an HMI, it can be a lot of things, right? Like a physical control panel with indicator lights bolted to a machine press, or an industrial PC with a touchscreen on a catwalk.
Or increasingly, it's a web-based interface monitored from a centralized control room miles away.
I like to use a car analogy to ground this. If a manufacturing plant is a car, the PLC is the engine block, and the transmission, actually generating the physical force.
Okay, I track with that.
And the SCADA is the onboard computer system tracking your long-term mileage and tire pressure. But the HMI, that's the dashboard, the steering wheel, and the pedals.
That is a perfect way to describe it.
Sure.
It's the exact point of interaction where you, the driver, manipulate the vehicle.
Right. And that translation layer is what allows operators to actually do the critical work.
Because in highly complex operations, like chemical mixing or power generation, you are dealing with a fire hose of raw metrics.
Just too much data for a human brain.
Exactly. The HMI parses those thousands of data points and translates them into readable mimic diagrams, vector graphics of the facility, and prioritized alarm states.
So it provides the situational awareness necessary to actually configure set points or optimize energy usage.
Right, and most importantly, it allows humans to manually override automated systems when the physical variables drift out of safe parameters.
Because the human operator is still the ultimate decision maker, but the HMI is the indispensable lens they look through.
They're flying blind without it.
So if the HMI is the steering wheel of our critical infrastructure, we really need to look at what happens when a malicious actor suddenly reaches over and grabs that steering wheel.
Which is a terrifying thought.
It is. Shifting into the NIST and PIATU guidelines on ICS risks, the fundamental paradigm of cybersecurity is inverted here.
Yeah, it's totally backwards from what most people know.
Right. In a normal IT network, the priority is the CIA triad: confidentiality, integrity, and availability. Confidentiality is king.
You don't want your data leaked.
Exactly. But in an OT, or operational technology environment, that triad is flipped on its head.
The primary concerns in OT are safety and availability.
Because if an HMI is compromised, the threat isn't that a hacker is going to download proprietary data and sell it on the dark web.
No, the threat is cyberkinetic. It is the digital manipulation of physical assets.
Which results in, environmental damage, the destruction of multi-million-dollar equipment, or literally the loss of human life.
The stakes could not be higher. And the mechanics of how these attacks play out on the screen are incredibly insidious.
Yeah, the sources made it clear it's rarely a hacker taking control of the mouse and wildly clicking buttons while the operator watches helplessly.
Right, it's much more subtle than that. Our sources detail techniques like manipulating alarm thresholds.
Oh, this part blew my mind.
So an adversary infiltrates the HMI software, right? And they alter the configuration files so that a critical temperature warning, which usually triggers at, say, 200 degrees, doesn't trigger until 500 degrees.
So the machine is actively melting down, but the HMI tells the operator everything is operating perfectly within normal parameters.
Exactly. You just don't know what's happening until it's too late.
And there's another highly sophisticated vector mentioned, the replay attack.
Oh yeah, that one is straight out of a movie.
It involves a threat actor positioning themselves on the network segment right between the PLC and the HMI.
They basically sit in the middle. They capture the network traffic reflecting a period of normal, stable operations.
And then what? They just loop it.
Yeah, they intercept the live data feed and play that recorded spoofed telemetry back to the operator's HMI screen.
So the operator thinks they're watching a live feed of a perfectly balanced system.
While in reality, the attacker is manually sending malicious write commands down to the PLC, forcing valves to close and pressure to build up.
Until the physical infrastructure just fails. It really is the exact mechanic from a heist movie where they luke the security camera footage so the guard doesn't see the vault being empty.
Except applied to a municipal water treatment facility.
Which is horrifying, and the window of vulnerability is shockingly narrow, isn't it?
Very narrow. The source material points out that if an HMI or SCADA interface is left accessible on the public internet with weak credentials, it gets found fast.
By those Shodan bots, right? The scripts that are just constantly scanning the internet for connected devices.
Exactly. They'll flag an exposed HMI in a matter of hours, not days.
Okay, but let me jump in here and play skeptic for a second on behalf of the listener. Because reading through these attack vectors, my immediate reaction was, why is a municipal water plant even connected to the internet in the first place?
It's a very common question.
I mean, I'm looking at these diagrams, and usually these highly sensitive ICS networks are supposed to be completely isolated. Doesn't air gapping, like physically removing any connection to the outside world, doesn't that solve this entire problem?
So the concept of the impenetrable air gap is actually one of the most dangerous myths in industrial security today.
Wait, really? A myth?
Yeah. I mean, while physically isolating a network is a good fundamental control, it is entirely insufficient on its own because it ignores the human element.
Ah, right. The human factor.
If you examine the most sophisticated ICS malware frameworks in history, like Stuxnet or Triton, they successfully compromised highly secure, supposedly air-gapped environments.
Because the perimeter is only as strong as the people who have physical access to it.
Precisely. The initial infection vector in those historical cases wasn't some remote hack over the internet.
What was it then?
It was a corrupted USB drive or a compromised engineering laptop brought into the facility by a contractor or an employee.
Oh, wow. So they just walked it right past the air gap.
Yeah. An engineer needs to apply a software patch to the HMI or maybe transfer a diagnostic log file. So they bridge the air gap temporarily with removable media.
And that's when the malicious payload executes.
Right. It establishes a foothold and uses zero-day vulnerabilities to propagate laterally across the OT network. A physical gap is basically useless if your protocol for removable media isn't locked down.
That makes a lot of sense. Plus, the Sorexio source highlights that the modern industrial sector is rapidly moving away from strict air gaps anyway.
Yeah, the industry demands connectivity now.
Right. Facilities want real-time analytics, remote monitoring, cloud-integrated predictive maintenance. HMIs are increasingly just web-based applications accessible via standard browsers.
Exactly. So if the network perimeter is inherently porous, whether that's through a USB drive or a remote access gateway, the security perimeter has to shift.
It sounds like the actual vulnerability isn't just the network boundary anymore, it's the human identity. How do these facilities track and control exactly who is standing at the terminal?
Well, that requires completely abandoning legacy security models.
Which were pretty lax, right?
Oh, historically, HMIs relied on shared generic operator accounts. A terminal on the shop floor might be permanently logged in as, operator station 3.
Or an entire shift of workers would just share a single password written on a sticky note.
Exactly. So if a critical parameter is altered or a system fails, the audit logs only show that the terminal sent the command. There is zero accountability back to an individual human being.
So it's the modern solution to that.
As detailed in the Automation View article on securing web-based HMIs, the standard now is role-based access control, or RBAC.
Okay, RBAC. This shifts the defense mechanism directly to the application layer.
Right. Modern facilities integrate enterprise identity provider systems like Microsoft Entra ID or Okta so that local passwords aren't managed on the HMI at all.
So every single interaction is tied to a specific authenticated digital identity using protocols like SAML or OpenID Connect.
Yaks-like. And under RBAC, privileges are strictly compartmentalized based on a user's verified role.
Right, so a junior operator might authenticate and only be granted read-only access to view pump telemetry.
But only a senior mechanical engineer possesses the digital permission required to actually alter the pressure set points or acknowledge critical safety alarms.
The technical implementation of this is where the Automation View source gets incredibly specific, and I found this fascinating. They highlight a vital distinction in web-based HMIs between front-end UI masking and back-end API authorization.
Yes, this is a huge technical insight.
I want to make sure I'm parsing this correctly for everyone listening. If we use an analogy, relying solely on front-end UI masking, it's like putting a piece of opaque tape over a critical emergency override button on a control panel.
That's a great visual.
You were just hiding the button from the junior operator's line of sight. But back-end API authorization is like going behind the panel, completely ripping out the wiring, and ensuring the button is dead no matter who presses it.
I enthusiastically agree with that analogy. It illustrates the vulnerability perfectly.
Because a hacker can easily bypass the visual interface.
Oh, easily. If an HMI developer only relies on front-end masking, the software simply hides the HTML element, the button on the user's screen based on their role.
But a malicious actor, or just an overly curious employee, can just open their browser's developer tools, inspect the code, unhide the button, and click it.
Or they can simply capture the network traffic and send the HTTP POSD request directly to the server themselves.
Because the backend server is just sitting there passively accepting any command it receives, it assumes that if the request arrived, the user must have been allowed to click the button.
Which is a fatal architectural flaw. The backend blindly trusts the front end.
So how do you actually secure it?
To properly secure an HMI, every single write action like changing a pressure valve must be intercepted and validated by backend middleware.
Okay, so when a user logs in, they get a token, right?
Yeah, they are issued a cryptographic token, typically a JSON Web Token or JWT, and this token contains a cryptographically signed payload detailing exactly what authorization scopes that specific user holds.
So before the HMI passes the command down to the PLC to open a valve, the middleware intercepts the API call, cracks open the JWT, and verifies the digital signature against the identity provider's public key.
Exactly. It checks if the token actually contains the specific write valve permission.
And if the scope is missing or the signature is invalid,
The middleware drops the request entirely, regardless of what the user did on the front-end screen. It ensures that the authorization logic is enforced at the server level, where the client cannot manipulate it.
okay, so establishing strong identity and back-end API authorization secures who is sending the commands.
Right, that's one massive piece of the puzzle.
But reading through the ABB Excellent HMI manual, it's pretty clear that securing the application login is only a fraction of the architecture. You have to build a digital fortress with multiple concentric walls.
Yes, which brings us to the ISA EC 624443 standard and the concept of defense in depth.
Defense in depth. I love that term.
It is the guiding philosophy of industrial cybersecurity. The premise is that threat actors will eventually bypass a security control. It's inevitable.
So if they breach the perimeter firewall, they must immediately encounter another distinct layer of security and another after that.
It's exactly. The ABB manual outlines 7 operational layers required to secure an industrial computer, beginning right at the foundational operating system level with system hardening.
Because if the underlying Windows environment running the HMI software isn't locked down, all that application-level security we just talked about is meaningless.
Completely meaningless.
Yeah.
The manual specifies full disk encryption, like BitLocker, utilizing a hardware TPM chip.
So if someone physically steals the industrial PC from the factory floor, they can't extract the configuration files or cryptographic keys from the hard drive.
Right. System hardening also involves systematically stripping away the attack surface.
Like disabling unnecessary background services, closing unused network ports, enforcing complex randomly generated passwords.
Yeah, and a critical element highlighted in the documentation is the configuration of Windows User Account Control, or UAC. They explicitly warn against setting UAC to never notify.
Why is that setting so dangerous? I mean, I hate getting those pop-ups on my personal computer.
We all do, but setting UAC to never notify is a severe vulnerability in an OT environment. It essentially grants permission for any executed process to seamlessly elevate its privileges to an administrative level without prompting the user for confirmation.
Oh, wow. So if a threat actor manages to drop a malicious payload onto the HMI, a silenced UAC allows that malware to just silently install rootkits.
Exactly. It can modify registry keys and completely compromise the host OS without the operator ever seeing a single warning prompt on their screen.
That is terrifying. Which brings up the challenge of updates. The ABB manual heavily emphasizes patch management, but also patch verification.
Yes, verifying the updates is crucial.
Because if a maintenance engineer downloads a software update for the HMI to fix a vulnerability, how do they know the installer itself hasn't been intercepted and poisoned by an attacker, like a supply chain compromise?
That relies on cryptographic hashing, specifically verifying the SHA-256 hash.
Okay, how does that work in practice?
Well, when a vendor compiles an update, they run the file through a cryptographic algorithm that generates a unique, fixed-length string of characters. That's the hash. It acts as a digital fingerprint for that exact file.
And because of the avalanche effect in cryptography, if a hacker alters even a single line of code in that massive update file to insert malware, the resulting hash will look completely different, right?
Exactly. It won't match at all. So before deploying the update to the live HMI, the engineer runs the downloaded file through a local hashing tool and compares the output to the official hash published by the vendor on a secure channel.
And if the hashes match perfectly, the file's integrity is mathematically proven.
Yes, and if they don't match, the file has been tampered with and must be isolated immediately.
The documentation also stresses the enforcement of secure communication protocols. It seems like a major vulnerability in legacy ICS environments is the reliance on old protocols like Modbus TCP.
Oh, Modbus TCP is a nightmare for security. It was designed decades ago for serial cables, long before cybersecurity was even a consideration.
Because it transmits data in clear text, right? And it lacks any inherent authentication headers.
Right. If a threat actor is on the network, they can easily read the telemetry and, more dangerously, inject malicious packets that the receiving device will just blindly accept and execute.
So modern defense in-depth mandates wrapping these communications in secure protocols like TLS or HTTPS.
Yes. The cryptographic handshake ensures that the traffic is encrypted, which prevents eavesdropping. And it authenticates the endpoint so you know the HMI is communicating with the legitimate PLC and not an attacker-spoofed device.
Okay, I have to pause here and challenge this architecture because I'm looking at this from a purely operational standpoint.
Okay, go for it.
We are talking about JSON Web Tokens, cryptographic hash verification, multi-factor authentication, TLS handshakes, identity provider middleware. As a user trying to log into a banking portal, that level of friction is annoying, but fine.
Sure.
But as an operator trying to run a high-pressure chemical process, what happens during a catastrophic emergency?
That is the big question.
Say a boiler is overpressurizing and is seconds away from a kinetic failure. The operator needs to hit the emergency shutdown right now. If the HMI prompts them to authenticate via a smartphone push notification or enter a 16-character password before it accepts the command, that IT security just caused a physical disaster.
You've identified the single most profound tension in industrial automation. It's the inherent conflict between IT security and OT safety.
Because they want opposite things in that moment.
Exactly. And the NIST guidelines address this directly with an uncompromising principle. Any cybersecurity measure that impairs physical safety is fundamentally unacceptable. Safety systems must operate deterministically and instantaneously.
Okay, so how do engineers actually reconcile that? How do you maintain defense in depth without creating a fatal bottleneck during an emergency?
By engineering systems for graceful degradation.
Graceful degradation, what does that look like?
The operational architecture must be designed to step down from highly optimized, secure digital automation to manual analog failsafes. If the digital HMI is locked behind MFA, or if the network is saturated by a cyber attack, or even if the server just crashes, the human operators cannot be left helpless.
But wait, are modern multi-billion-dollar smart factories actually still relying on physical analog switches? I mean, it seems almost counterintuitive to build this massive digital infrastructure and then just wire a big red lever to the wall.
They absolutely rely on them. They're known as Safety Instrumented Systems, or SIS.
And they operate completely independently.
Entirely independently of the basic process control network. These are hardwired analog circuits and physical relays connected directly to the mechanical actuators. They bypass the HMI, the SCADA network, and the PLCs entirely.
So in the event of our hypothetical boiler over-pressurizing, the operator doesn't even need to log into the HMI.
Exactly. They just pull a physical breaker that mechanically cuts the power to the pumps. The HMI provides the daily operational efficiency, the predictive analytics, the secure configuration, sure, but the ultimate preservation of human life relies on a physical handbrake that cannot be hacked, spoofed, or locked out from a keyboard half a world away.
That is deeply reassuring, honestly. As complex and opaque as the digital layers become, the final layer of defense in depth is really just physics.
The physical reality always takes precedence.
Synthesizing all of this, we've mapped out some incredibly complex terrain today.
We really have.
We've looked at the architecture of industrial control systems, identifying the HMI as that vital translation layer that makes massive volumes of raw machine data comprehensible to humans.
Right.
We've examined the severe reality of OT security, where vulnerabilities like manipulated alarm thresholds and replay attacks can bypass air gaps via human error, leading to, cyberkinetic destruction.
Which is the real nightmare scenario.
Exactly. And we've detailed the engineering response shifting from legacy network perimeters to identity-based perimeters using RBAC and back-end API authorization while layering OS hardening on top. All without ever compromising the analog fail-safes that guarantee human safety.
It is a relentless, constantly evolving engineering discipline. The methods of securing the HMI just have to adapt to the sophistication of the threat landscape.
And looking at the horizon of that evolution brings up one final detail from our sources that we should leave everyone listening to ponder on their own.
Oh, this is a good one.
The Surexio Guide touches on the next generation of HMIs and the integration of artificial intelligence. Modern industrial interfaces are beginning to leverage machine learning models to analyze historical telemetry and actively intervene, like optimizing processes or correcting anomalies, before a human operator even registers a problem.
It introduces predictive, automated decision-making right at the interface layer.
Right, but consider the security implications of that. If the HMI transitions from a passive screen that strictly takes authorized orders from a human into an active system making its own automated operational decisions based on AI algorithms, how do you secure a system where the line between human intention and machine action starts to blur?
It's a huge unknown.
If an AI model decides to shut down a pipeline but the human operator disagrees, how does the system resolve that conflict? How do you grant cryptographic authorization scopes to a predictive algorithm inside a role-based access control framework?
We are rapidly approaching a paradigm where the human-machine interface essentially becomes a machine-machine interface.
It redefines the entire concept of access control and trust in critical infrastructure. We will leave you with that to mull over. The next time you turn on a tap, flick a switch, or rely on any piece of modern infrastructure, remember the invisible screens parsing millions of data points and the incredible digital fortresses engineers are building to keep the lights on and the water flowing safely.